So I'll just begin by showing the slide that we ended with yesterday. Hopefully, some of you have done this. Have you at least attempted some of these questions? How many of you have attempted at least some of the questions? Okay, fine. Let's just quickly kind of run through. Like, anyone can tell me the answer to the first question? The average degree of this network, right? So this is a simple, well, smallish network. What's the average degree? Close. Huh? No. No. Okay, it's 2.6. You can look it up. What about the shortest path length between nodes 3 and 4? Yes. Okay. The diameter of the network? 4. Right. What is the number of walks of length 5 between nodes 2 and 3? Number of walks of length 5 between nodes 2 and 3. So remember, a walk, you can actually go back along the same path.
4.
5.
Hits 5. Yeah, because remember, you can actually cross the same link multiple times in a walk. It's not a path, right? So yes, the answer for this is 5. Anyway, you can work it out. Number 5. Okay, so the clustering coefficient of nodes 1 and 8. Okay, how about node 1? What's the clustering coefficient? So one has like who's the neighbors? It has 6, 5, 9, 4, and 8. Those are the neighbors, right? So and how many of the neighbors are connected? Not 1 by 6, no. 1 by 10. Yes.
10. Yeah, 0.1.
1 by 10. 0.1. Yeah. And then what about 8?
0.3.
Yes, exactly. 1/3. Yeah. And okay, so the last two are a little bit harder. Okay, you have to do a lot of counting. So how many of you have attempted to do 6 and 7? Or has anyone? Okay, can anyone say the answer for number 6?
0.243.
Very close. Very close. Anyone else? So okay, so no other guesses. Okay, so the answer to that is basically you have two triangles, right? So remember, let me go back to the definition. The global clustering coefficient. Yeah, right. So basically, so that's the definition, right? So 3 times the number of triangles divided by the number of connected triples, and a connected triple is basically any path of length 2, which is either closed or not closed, right? So basically, in this network, you say 2, 4, 5. That forms a connected triple, right? Then 4, 5, 3 is a connected triple, and so on. And here you're not considering the directions. I mean, that's already taken into account in the formula. So it's only 3, 5, 4 and 4, 5, 3 are the same. There's just one connected triple. So the answer is you have two triangles. Sorry, you have two triangles, and if you do the counting, turns out that you have 27 connected triples, right? So the answer is 3 times 2 by 27. So you may be wondering, okay, so is there a simple way to do this? Yes, there is a very simple way to do this, and so that is, so remember, no, sorry, not this one. Yeah, so remember this, right? So this tells you the total number of walks of a given length, right? So if you want to find the walks of length 2, I just take the product adjacent matrix times itself. So if you do that, then you'll get all the walks of length 2 from every node to every other node. And you ignore the diagonal because the diagonal is not a connected triple, because you're going from one node to another node and back to itself. That's not a connected triple. You need to have three nodes. So you can ignore the diagonal, and then you just look at all the other entries in the matrix. You just sum them, right? And then yeah. So basically, that's like a quick way to do it. So you can work that out, and then quickly getting to the last one. Between is centrality. So this was also very hard because it will take some time, but has anyone managed to do this?
0.07.
0.07. No.
3. Okay.
Anyone? No. Okay. So the answer basically for node number 3, the answer is 2.5, and the answer for 4 is 7.5. Okay. So now you may be wondering, okay, how do you do this? Well, there is no real simple way to do this beyond counting, but remember I had talked about this technique, this breadth first search. Yeah. So if you follow this, then basically you can make a list of all the paths, right? So basically I know I go from 1, so I go from 7, I can go have a path of length 1 to 6, 5 and 8, and then I know, okay, then from 5 and 6 I can go to 4, 3 and 1. Okay, I can go from 5 to 4 and go from 6 to 3, 6 to 1, and so on. So then basically I can list out all the possible paths. Now this is something which you will have to do on the computer, because this is not something that you can count so easily. But if you follow this, then this way you can kind of get all the strings basically that tell you the paths going from one node to another node, and then you say, okay, following this what I mentioned over here, you just count basically. Oh, this one, right? So basically you just say, okay fine, so how many times does a given node appear in the or the fraction of times that it appears in all the path lengths between other nodes, right? So remember we went through this. Oh, I forgot to fix this. This should be 2. There should be an extra plus 1 over there. I'll fix that. Yeah. So basically you follow this, and so basically so now the first table you would have got from your breadth first search, and the second one you can just it follows very naturally. So that's how you would do this. Okay. So anyway, so let's stop with that. So hopefully you can try that out later if you haven't tried it yourself. Okay, so now let's start with today's talk. So, where's my, yeah. So what do these two people have in common? So first of all, hopefully both of you, you know who both these people are. Yes? Okay, who's this person? Okay. Kevin Beck, yeah, thank you. Okay, I'm not that old as you. Okay, so yes, and this is, okay. So what, can anyone guess what these two people have in common? They are kind of celebrities, yes. Sorry?
Similar facial structure.
Similar facial structure, okay, I never thought about that.
Now that he mentions it, yes. So Kevin Bacon can play Adosh in the next birthday.
Yeah. Okay, anything else? Birthday? Okay, I'm not sure actually. I just get a number thing? Okay, yes. That's right. So basically, what sort of unites them in a very strange way is that both these celebrities are well known for in the popular imagination for the concept of what's generally referred to as 6 degrees of separation, right? So in the case of Kevin Bacon, some people who just playing around with like the sort of database of the actors and who was acting in which movie and so on. They're constructing these networks, and then they realize that you can get from him to basically anybody else in Hollywood with just a few number of hops. So he's in a film with this person. This person's in a film with this person, and you can do this for basically anything. So of course he hasn't acted in every movie. Of course he acted in a limited number of movies. But if you look at the person who he acted with, it's a fairly reasonable pool. But then you look at who they acted with, and then who and so on. You find that, well, I've basically spanned almost the entire Hollywood, right?
You have spanned almost everyone who has ever acted in a
more or less. I mean, that's basically, yeah, true. I mean, you can even go beyond Hollywood because you've had international collaborations and so on.
Yeah, I remember like during 2000, Ambedkar was giving a talk on it. So this is just 2 years after Strogatz's famous statement.
Right.
And he asked this question like, what is Madhuri Dixit's taken number?
Oh, okay.
It turns out it's 5.
Wow. Okay. Yeah. So, but anyhow, the point is, I mean, there's nothing special about Kevin Bacon, right? It's just that it sort of gained popularity when people pointed this out. But you can actually have a Bacon number. Or, so this is what, as you said, a Bacon number is basically how many steps do you need to go to reach him, basically in terms of collaboration. But you can have a Bacon number for anyone. You can have a Bacon number for Patrick Stewart, and it will be more or less the same. It's actually, it's not a property of the number of movies he's acted in or anything like that. It's a property of the structure of the collaboration network, you could say, right? And so similarly, Erdos, like he is well known for. I mean, so his name is sort of been popularized in the concept of the Erdos number, right? So you look at the people who he collaborated or he wrote a paper with directly, right? So let's say he wrote a paper with this person. This person has an Erdos number of 1, and then you see, okay, so who are the people who this person wrote a paper with? This person has an Erdos number of 2. He's not. This person has written a paper directly with Erdos, it's an Erdos number of 1, and so on. But then you can see who is this person written a paper with, and assuming they have not written a paper with anyone with Erdos number 2 or 1 or 0, then they have an Erdos number of 3, and so on. And one can actually find out over the whole sort of maths community. And even you can say the broader scientific community, like what is their Erdos number. So it tells you in some sense how kind of how connected the community is in terms of collaboration. Like how people talk to each other, how people sort of how they collaborate. So anyhow, but this was, I mean, they're both just fun concepts. But the main sort of point behind this is that in real networks, there is actually it's actually a lot more sort of dense than we think. Dense in the sense of like we can actually get to someone completely unexpected by just a few steps. I know somebody, he knows somebody else, he knows somebody else, so he or she knows somebody else. And then it says, oh, the person who I know knows the prime minister or something like that, right? So it's quite amazing, and in fact,
The question is, would someone who have finite Erdos number also have finite Kevin Bacon number?
I think no. Yes, there is someone I remember who actually has both numbers. I think.
It means that the world of mathematics is connected to the world of
Yes.
If one person has a finite Bacon number and a finite Erdos number,
Yes.
now even if you have a finite Erdos number, then automatically you will also have finite.
Yeah, that's true. Yeah, I remember reading about that. So someone who was an actress. As an actress, she basically she then did some research, and then she has an Erdos number as well. So yeah,
Natalie Portman.
I guess so. Yeah.
Now that would happen via Donald Trump. Right? He's friends with Elon Musk.
Yeah.
I'm sure there is a bunch of
Donald Trump himself has appeared in movies.
Yeah, that's
Yeah,
what
that's
I'm
what-
saying. On
yeah.
the other hand,
Yeah.
he would have appeared in
Yes. Anyhow, so the point is, yes. So the point is that in real social networks, you can actually, it's quite remarkable how you can get from one person to another person in just a few hops. And in fact, this is something which has been in the popular imagination for a very long time. So there was this sort of a play that was written, I think a short story written by this Hungarian author from the 20s, where basically he kind of describes a scene wherein he needs a new car, and he's saying, okay, how do I get this car? He says, basically the worker knows the manager in the shop, and the manager knows Ford, and Ford is in friendly terms with the general director of Hearst Publications, who is good friends with somebody who is a good friend of mine, right? So basically, I asked this person to send a telegram to the director, to tell Ford, to tell the manager, to tell the worker to quickly hammer together a car for me, as I happen to need one. So he's saying it's so simple. I can.
I'm sorry to say, but Indians know this concept way earlier. It used to be,
Yeah.
I need to get a take train ticket to go tomorrow for some interview.
Yes.
I would ask my father,
Yes.
who would ask his friend, who would ask his son-in-law, who would ask his uncle.
Yes. Yeah. No, so
So Indians have been very good at cracking this.
for sure. I mean, it's. I mean, like I said, this is. It's just a sort of almost a natural property of social networks. You know, it's which is just something which it's only recently we've begun to appreciate a little bit more, especially quantitatively. You know. But yeah, and then so the term actually only got popularized in the 90s with this other play called 6 Degrees of Separation, where again he sort of talks about the same thing. But again, this is something which we all sort of intuitively know, right? So you know, we can actually you know, have pretty unexpected connections by just a few hops, you know. But how exactly do you kind of show this like more sort of rigorously? So for that there was this experiment that was done. It's called the Milgram's experiment. I think it was in the 60s, and so basically what he decided to do was, or his team decided to do was, they said that okay, so let's find a random specific target in Boston, and we want some random people in Kansas and Nebraska who at that time they be looking for. It's pretty unlikely that these random people are going to have any connection to somebody in Boston who they have chosen. And so what they did was they just send like a package which is sort of giving the details of the experiment, saying that basically we want this is the goal of this experiment, and they said that they mentioned the name of the target. They said that this is this person in Boston, and this is his address, this is his occupation, so on. They gave some details, and then they said that okay, so what you need to do, the recipient of this package, what you need to do is you need to mail this to somebody who you think is likely to know this person, right? You believe the person who you're mailing it to is likely to know this person. So obviously they're only going to mail it to people who they know. That's only, you know. So they'll send it to someone who they know, and the same package will have the same instructions, right? So the person who receives that package is now going to have to do the same thing. Say, okay, fine, this is the person in Boston. Who do I send it to, right? And what he wanted to check was how many steps do I need, and of course every time it got sent, it was marked, okay, step 1 step, 2 step, and so on. So they said, okay, how many steps do you need to go in order to reach the target, right? And so they had like a bunch of, so these 6 out of 296 individuals, 64 of them reached the target. You could say maybe that was not a, you know, huge, well, it's not too bad. So 64 reached the target, and of the 64, it turns out that by and large you see that you arrived within 4 to 6 steps, right? So this is just a sort of an example route of how you know the package could go from Kansas to Iowa and so on, and just a few hops, and then it would reach its target. Now, why exactly is it's going along this particular path, and why not a more random path? Well, that's, you know, it could, right? It just so happened that along this path the people tended to know people more towards the east, but yeah, it can go on a much more random path as well. So you know, the path is not important. What is important is the number of steps, right? So yeah, anyway, but the point is that so the average path length was around 5. So this is kind of remarkably close to you know, this notion that, you know, just within around 5 or 6 steps we can get basically from anyone to anyone, right? So this was actually a very interesting work that was done from this perspective. Okay, so
Shakti,
yeah.
like why is it like 6 degrees of separation? How did the 6 come?
How did the 6 come up? That came from the play, and I don't, and
There's a very simple-minded argument. So, you know, like, let's say you know 100 people. Okay? So those 100 people each know 100 other people. So second order of remote, you know 10 per 4, right? So in this way, you figure out in how many hops you know billion people.
Right, yes,
That's the
right,
population
right.
of the planet. That is a big fallacy. The fallacy being, the 100 people I know, they each don't know 100 separate people.
Yes,
Okay? So that was a big mystery, that this will only be true for a random network where there is very low probability that 2 people I know would also happen to know each other. So cycles are very rare in random networks. In real life, because of clustering, this is not true. So there's a lot of clustering. So the big mystery was this random network argument gives you a quick back of the envelope calculation which says that you should by a maximal path length, the diameter of any social network would be about 5 to 6, given the population of the planet. And yet it is assuming random network. Right? So the question was, why does it work so well when our social networks are not random? And that is precisely where Strogatz's argument comes in,
Right.
who shows that we could have high degree of clustering, but a few random shortcuts would make it effectively look like a random network with a global scale.
So, I mean, that perfect segues into what I'm just going to mention now, which is that, uh, this fact that you can get from anywhere to anywhere else in this network in just a few number of steps clearly seems to be like something that is seen in reality, right? So it was not random. If it was random, so then you could sorry. What am I saying? So you could say, okay, fine. In a random network, you can actually go from. The average path length is can be small because basically you can have a lot of shortcuts, right? But the problem with the random network is that the clustering coefficient. Remember we talked about clustering coefficient earlier. The clustering coefficient is not going to be very high, right? Because if I know somebody and that person knows somebody else, then you would expect at least in a social network, you expect that, okay, maybe I also know that other person, right? That's how things tend to be seen in reality. But if it's purely random, then that may not be the case, right? So in a purely random network, it would have a low average path length, low average path length and a low clustering coefficient. Um, uh, yeah. So sorry, there's a typo over here. So there should be high average. Yeah, sorry, there's a typo over here. So basically, random networks have a low average path length, and a regular graph, right? So a regular graph where you see something like this, where like you have some neighbors, and their neighbors have some other neighbors, and your neighbors and your neighbors are likely to be connected amongst each other, right? And so on. So this has a high clustering coefficient, but it has also a very high average path length, because if I want to go from here to here, I may have to take a large number of hops, right? So it'll take a long time for me to reach two random points in a network compared to here. So yeah, so I'm sorry about the typo. So basically, this has a high average path length. So basically what Watts and Strogatz did is they said that, okay, so clearly in reality you would see the networks have a kind of a combination of both. It has a clustering coefficient that is on the higher side and an average path length that's on the lower side, right? So how does one arrive at this? They suggested this following procedure, which is basically that so you just start with a regular graph like this, okay? And so every node has k neighbors, let's say. And so what you do is you cycle through every node, and then you consider the k by 2 rightward links, so just the links towards the right, and then you randomly rewire these links with some probability p, avoiding of course self loops and duplicate links. Okay, so just by doing this simple procedure, what they found is that so remember here you have for a regular graph you have a high clustering coefficient and also high average path length. And for a random network, both of them are low, right?
What is a regular graph?
A regular graph basically, so it's one in which the nodes, so every node has basically the same kind of neighborhood structure. So basically, if I look at the neighborhood structure of this node and the neighborhood structure of this node, it looks exactly the same. So in some sense, the labels are interchangeable, right? Whereas if I interchange the labels on this random network, it doesn't make sense. So so this is what happens at the two extremes. But if one gradually increases p, going from p equals 0 to p equals 1, what one finds is that, okay, so as expected, the average path length is going to reduce, right? That's not surprising. But the clustering coefficient, it doesn't drop as fast. So it drops much more slowly than the average path length does. And so what that means is that there's a sort of an intermediate region of p, right? So a range of probabilities for which you have networks which have high clustering coefficient and low average path length, right? So you have a network that looks something like this, right? So you basically it's for the most part you have neighbors whose neighbors are also neighbors, but you also have like these kind of shortcuts that help to sort of reduce the average path length. And so these type of networks are essentially referred to as small world networks because they kind of have this sort of small world structure, right? Yeah.
What exactly is P?
P is basically, yeah, so it's the probability by which you rewire the links. So basically you cycle through all the links. So basically you start with the given node, you just go let's say clockwise, and then you look at all the rightward links, and then you just rewire them. So basically you consider every link uniquely, and with some probability you rewire them, and the probability is what is your parameter. So okay, so yeah, so this is the small world network, and as we were just discussing before, you can do a lot of interesting sort of and a lot of analysis has been done on this network, especially when you have spins or I'll talk a little bit tomorrow when you have games on networks like this as well. But anyhow, so that's for tomorrow. But yeah, so this is basically what Watson Strogatz did. So now I will talk a little bit about some other types of random networks briefly, and then get to the organizational structure of networks, specifically like modularity and so on. So let's first look at random networks. Okay, so when one thinks of like a random network, typically this is the model that comes to mind. I mean, this model has which was developed in around 1959, 1960 by these people, Erdos and Rennie, although Gilbert had also independently worked on this. Is a very simple model to generate a random network, and it has some very interesting properties. So basically what you do in this model is basically you say that suppose you have a group of n nodes, you just connect each pair with probability p. That's it, right? So it's a very simple algorithm, and you end up with some network which may have multiple connected components depending on the specific choice of n and p. And remember, we talked about what connected component was earlier, right? So basically, suppose I am in this component, I cannot get to another component over here. I can go anywhere within this, but I cannot reach that component, right? So these types of networks are what typically in the literature are referred to as Erdos-Rennie networks. And so these networks like this, they provide a very good benchmark for doing a lot of analysis, because the assumptions underlying this are extremely minimal, right? So suppose one wants to ask a question regarding, so for example, like you know, if you want a network of a certain average degree, you can just choose your n and p accordingly and say, okay, fine, but with this choice of n and p, I will have a resulting random network with such an average degree. And then you can study the properties of such a network, you can study dynamics on the network, you can do whatever, do all your analysis. And then you can ask the question, okay, so how much of the behavior that I'm getting in this random network is matching what I'm seeing maybe in some empirical network, right? And if you find a mismatch, then you say, okay, fine, then it's not strictly because of just the average degree, there must be some other constraints. Maybe there is some other organizational structure which I'm missing, or there's something else, right? So this provides a good benchmark to start in a lot of your analysis. Okay. So one thing about this network is that for a given network, you can actually, so if you look at the total number of connections coming from each node, so that's the degree, you can actually find that these types of networks have a specific distribution in terms of their degree. So what is the distribution? So suppose you have a network of n nodes, right, which is generated through this procedure, that has independent probabilities of connecting to each of the other n-1 nodes. Okay, so that is exactly how the ER is defined. The ER is Erdos-Rennie network. So the probability of connecting to k of such chosen nodes and not the remaining nodes is basically just the product, right, of this. Basically p per k and times 1 minus p, basically not connecting, power, and remaining nodes is n minus 1 minus k, right? So You get that, right? So basically, so you have independent probabilities of connecting or not connecting to any of the other nodes. So that is basically this. And there are also, we know that there are n minus 1 choose k ways of choosing the k of the n minus 1 nodes, right? So because which of the k nodes are we going to connect to? So that's given by this, right? And so therefore, the probability that a node in this network is going to connect to k nodes is given by this, right? And this is what is known as a degree distribution. So it just tells you what is the probability that a randomly selected node in the network is going to have a certain degree k. So suppose I pick a node from the network, what is the probability that is going to have a degree 1 or 2 or 3 and so on. And so that is given by this formula over here. And you will see that this is just basically the binomial distribution. I guess most of you know what a binomial distribution is. Yeah, so this is basically just the binomial distribution. So for large values of n, for basically a large system size, you find that an heterogeneous network, it just has a binomial distribution in terms of its degrees. Okay. But you could say that, well, not all networks are going to have a distribution like this. In fact, not all, very few of them do, right? So there could be other types of degree distribution that one might observe. And so for that purpose, there was another approach. I think it was, so this was initially done by Price in the 60s or in the 70s, and then but it was more sort of there was more work done by Barabashi and Albert on this, and basically this is an approach by which you can generate a specific type of degree distribution, which is called a power law distribution, right? So in a power law distribution, so you see here that along the x and y axis, I've just shown, rather than p of k versus k, I've shown log of p of k versus log of k, right? And it will follow something like this. So it will follow like a kind of a straight line like that, roughly, and with some slope, right? So basically, it will follow k power minus gamma, where gamma is the exponent. So this is what is a power law distribution, and it turns out that by following this procedure, which I'll just mention in a second, you can obtain networks that start to have a distribution that's close to a power law, right? And so these networks are what are called scale-free networks. And so the mechanism that you use to get these networks is what's called a preferential attachment mechanism. So what the mechanism is as follows. So you start off with some m nodes in the network, and then you sequentially add nodes to the network, and you can each node will connect to m random nodes. So amongst this set, it will connect to m nodes at random with some probability, and the probability which it connects to the nodes is given by this. So basically, so the probability that it connects to, let's say, a node I, is just basically the degree of I, which means, okay, the existing degree. Suppose, let's say I have a node over here. This node has 1, 2, 3, 4. Okay, so basically this will be 4 divided by the sum of the degrees of all the nodes, right? So what does that mean? That means that if you already have a high degree, that means that the probability that a new node is going to connect to you is high, right? Whereas if you have a low degree, the probability that a new node connects to you is lower. So if you keep adding nodes to this network sequentially, what you'll find is that nodes with high degree tend to get an even higher degree, right? And this kind of cascading kind of effect is what leads to something like a power law distribution. So you have a few nodes, very few nodes with extremely high degree, and a lot of nodes with a very low degree, right? So that's basically what you see over here.
What is the summation term in the denominator?
Oh, it's just the sum of the degree of all the existing nodes, right? So basically, the ki is the degree of the node which you've chosen. So, and then this is just the same, looking at all of it. So which means that the node with the high degree is going to have a higher probability of being connected to. So if ki is just 1, then it has 1 by a lot. But if it's 5 or 6 or something, it has a.
The overall degree of the network of the other nodes is higher, and the probability would be low.
No, because this is just a, what's it called, the probably low for what exactly?
If the other nodes are more connected.
Yeah, it's not. So if another node is not connected, it will have a higher ki, right? So it just depends on the ki, right?
The node other than I.
No, I is not the node which you're going to connect. I is the node which you're going to connect to. Right? So suppose I want to connect two nodes, I'm bringing a new node in. So this new node, am I going to connect to node I or not? And so that, yeah, so this new node has no degree. It is just coming in and says, should I connect to node I? And that probability is given by this.
Right? Can J ever be equal to a
J, yeah, this is over all of them. Yeah. It's just the total. So, yeah.
Also, what is scale free about these apps?
Yeah, that's just the term that's being used to describe this. Basically, it's sort of used interchangeably, Pavlov and scale free sort of things. It's just to say that, you know, like regardless of the, you know, you see the same property over like a range of k. It follows this what's it called? The same slope is going to be same. So okay, so anyway, so that was just a brief discussion about scale-free networks. Now, just before I get to modular and hierarchical networks, I'll just quickly mention another sort of. Unfortunately, I don't know if you can see. Oh, it's a bit. I'm sorry, it's a bit too faint. You should be able to see like a blue over here as well. So basically, what I wanted to mention very quickly is that one way that one can deconstruct like a network is in terms of what's called the core periphery structure, right? So the idea is that networks typically, or it might have a certain sort of subgraphs, it might have a certain, basically component which is within that is very highly connected, right? Okay, so let me explain. I think it will become clear if I explain this. So like a K core is the set of nodes of a network within which each node has it should be at least k links with each other. So it has at least k links with each other. No, sorry, it has it has at least k links with each other. So for example, over here you see that basically all the nodes have at least one links within with all the other nodes over here. So here this has a link, has one link. Okay, fine. This is just the what's called the one core. Basically, I mean, it's almost this is the network itself. It's very obvious, right? But you notice that these nodes which I have labeled as one, I mean, they obviously they don't have two connections. There's only one connection. So they are not part of the two core. Whereas on the other hand, all the remaining nodes over here, they they have at least two links, right? So suppose I've discarded like the ones out of the picture, right? And you just look at what's within this red sort of region. You see that within the red region, you see this 2 has 2 links over here. I'm just going to ignore this link over here because that one is no longer there, right? So this has two connections. This has 2. This has at least 2, and so on, right? So, but now if I want to say what's the 3 core, so obviously this and this have to be discarded. Now look at these remaining nodes and say, okay, fine. So within these, they have 3 links, right? At least. So 1, 2, 3, 1, 2, 3, and so on. Again, I'm ignoring this link, this link, this link, this link because I've excluded the nodes that are part of the 2 core, right? So and you can't go higher than this. So ultimately, this portion of the network has got the what's called the highest K core, which means you cannot you cannot have a core of the network with the 4 connections. And so this is what is referred to, the nodes of this is what's referred to as the core of the network, and all the remaining are called the peripheral nodes. And so yeah, so this is basically a technique to try to identify which part of the network perhaps you could say is more central in terms of in terms of the organization, right? So basically it's like everything sort of seems to sort of kind of a lot of the processing, or however you want to interpret it, will be happening within this region. Of course, it is going to depend on the specific context, the kind of network you're looking at, and so on. So yeah, but of course that analysis is sort of not going to get into here.
If I start with 2 here, then
yeah,
shouldn't 2 belong to 3 core?
No, because I'm going to remove the ones, right? So you can imagine now I've plucked out all the ones, and now the 2 has only 2 connections left.
So we start with like 1 core, 2 core.
Yes. So you start with 1 core, and then you say, okay, fine, these nodes have only 1 connection. I plug them out. And so now look at the network that's remaining over here inside the red, and say, okay, fine. So within this has 2, this has 2, and so on. So this link over here I cannot consider because it goes outside the core. Yeah. So anyway, so that is with regards to cores. Okay, fine. Now finally, yep. Okay, so now I will get to modularity. So modularity is actually a very interesting sort of component of network structure, wherein uh, no, nodes that exist within certain groups tend to have more connections within the group compared to connections outside the group. Okay, so for example, you see a network over here, and they're sort of colored according to like whichever group that they belong to. You see that within these groups you have a lot of connections, but across the groups there are not that many connections, right? And it turns out that in reality a lot of networks tend to show this structure, right? So like you can think of many examples, right? So basically like let's look at say the friendship network of students, right? You will have a lot of connections within the students belonging to a given institute, maybe a few connections from another institute, then another lot of connections within another institute, and so on, right? So this is something that I mean, one can think of a lot of examples like this, where basically you have a kind of a community structure. Basically, you have groups wherein within the groups there's a lot of connections, but very sort of sparse connections outside the group. But of course, now the challenge is going to become how does one know whether or not A, that the modules exist, and B, like what exactly is the organization, right? So how does one say how modular a network is, and what are the modules? This is actually a very non-trivial sort of question, because essentially what you have to do is you have to first specify, okay, let me, because had this not been colored and had these nodes been just organized at random, right, it would be very difficult to say this. It's almost impossible, I mean, just at least visually looking at it. So one needs to have some procedure to basically firstly figure out like what the groups are, and then is the density of interconnections within that group more than that across groups. So this is sort of an iterative kind of procedure, and it is a non-trivial question, right? So how does one actually do this? So there are many approaches, but like let's start to let's look at a very basic way of doing this. So you can quantify the extent to which the communities in a network are segregated by first considering the following. So let's just say that if Gi is the community that a node I belongs to, then the total number of edges between the nodes belonging to a given community, let's whether it is G1, G2, G3, and so on, the total number of edges between these nodes is basically just this, right? So by the way, I forgot to mention this yesterday. This is just a delta function. So which is that if the two sort of coefficients are the same, then it's 1. So suppose this is Gi is equal to Gj, then it's 1. Otherwise, it's 0. So basically, it means that if node I and node j belong to group 1, then it's 1. Otherwise, it's 0. Okay. So you can see very trivially that if you multiply the adjacency matrix by this, which means you only consider the connections within each group, group 1, group 2, group 3, right? Then the total number of edges is basically that, right? Half is because the adjacency matrix for the undirected and the network, you're double counting. So anyway, you have this, okay? So now let's just say that so the total number of links in the network is m, and one can imagine you have 2m stubs, okay? So let's just say you have a network like, so you have a very small network like this, you have connections like that, and you have these are stubs, okay? So if all of the links were just randomly assigned, okay? So let's just say that, okay, so I'm just going to I know that each node has each node I has some ki stubs, okay, and then I'm going to just assign the links at random. Then what will be the expected number of links between stubs of node I and node j? Well, that's very simple. So that's basically just ki times kj by 2m, okay? That's clear, right? So basically, so because if a node, let's say a node j has kj stubs, and in total there are 2m stubs, right? Then the likelihood of a link, so just going to drop a link, and the likelihood of a link going and attaching to a stub is just basically kj by 2m, and the likelihood of the other end of that link going to node I is basically, so since you have ki stubs, so that the expected number of links between the two is just this, ki times kj by 2m, okay? So the expected total number of links, expected if it was purely random, between nodes belonging to the same community is actually should be this, right? So basically ki kj by 2m times this one. So basically this is just again to ensure that you are within the same community. So if you are within the same community, this is what you would expect to see, not this. So you have this is expectation and this is reality, right? The normalized difference between the actual and expected number of edges between the nodes in the same group in an undirected network is basically that, right? So basically I'm just taking the difference of the two, and this difference and this normalized difference is what's referred to as the modularity, okay? So the modularity is basically a measure of the excess number of links that you see within the groups than you would expect by pure chance, okay? So if it was purely by chance, it should just be this, and so but it's not. Or it may not be. You might find that that actually I'm getting more connections within the group than would be expected by chance. So this will have some positive value, right? I could have the opposite as well. You could have what's called an anti-modular network, where I have less connections within the group than would be expected by chance. But I won't get into that today. But in principle, you can also have such a network as well, and it can be described with exactly the same quantity, yeah, the Q. I mean, I won't. Yeah. Yes. Yes. Suppose it was purely random. What would it be? So this is the empirical, then this was what would be had it been random.
So is the group really?
Okay, no. So this is if you know what the group is.
Yeah.
If you know the group. So yeah, I'll come to in a second. The question is, how do you find the groups? So if you know what the groups are, then one can say, okay, what will be the Q? In fact, that is exactly one of the big problems, to find what the group is. If you know what the group is, then you can say, okay, this is what the Q is going to be, right? Okay, so yeah, and just I won't get into it, but one can do exactly the same thing for a directed network as well, and one can see that this is the case. The 2 is cancelled because because now you have a directed link, so it can only point in one direction. So there's there's an extra half over here, so the 2 goes. Okay. So now, so the point is, you have this quantity which is called the modularity, which one can define, which one can use if you know what the groups are. So how do you now find the group? So how do you find the modular structure? So one of the most common approach, there are many ways which people have. In fact, this is actually a very non-trivial kind of problem, and people have many different approaches by which they can try to solve this question. But one very commonly used approach is what's called modularity maximization, because since you know what the Q is for a given group, you would think, okay, fine, I just have to make sure my Q is maximized. Now that itself is not straightforward to just maximize Q, but you can say, okay, hypothetically, if I can maximize my Q, then I have found the best possible sort of partition that exists, right? Because in principle, like let's just say I go back over here, right? And I take this blue node out and I make it red. Okay, so now this blue node has gone over here. It's still a modular network, if you think, because by and large, you see there's a lot of connection between red, between yellow, but except now this one blue has gone over here. So maybe it's making it slightly less modular, right? Or at least this organization is a bit less modular than this particular organization. So in some sense the Q is not a statement about the network itself, but about the organization, that the organizational structure which you have uncovered. You say, suppose we can segregate this network into these communities, and this has a certain modularity, right? So so that's the point I wanted to stress. So anyway, so the point is, you can try to maximize the modularity. So basically, just try and figure out what should be the organization that gives me the maximum Q. You see, this appears to be the optimal kind of partitioning that exists for this network. So so I won't get into the details of this, because there are quite a few steps involved. But to just tell you the basics of this is that essentially what you can do is that you can just write down the same Q just like this. So essentially all I've done is I've just exchanged the delta function for this, where I've like, let's just say I have two groups, and I just assigns +1 or -1 based on which group that the node belongs to. And so then you can see that if both of them are the same, both are +1 or both -1, then this whole thing just becomes 1, otherwise it's 0. Okay, so it's the same as just that what I had earlier. And it's easy to see that basically this is just equal to this, basically, because if you just have if you did not have this SIH, you just had a 1, then you will find out that this actually is 0. This I'll leave it as an exercise to you. It's very simple. That without this term over here, this is just 0. Okay, try and work that out. And so then you would get this, and you can write what's within the brackets as some matrix Bij, right? So basically Bij is just what is here within the brackets, and this S, like I can just, if I define this as some column vector, which is basically telling me, okay, +1 or -1 depending on which group it belongs to. You find that this is just nothing but like this particular product, basically matrix products, basically S transpose times P times S. Again, one can work this out very easily. It's just trivial algebra. So now, given B, so B is basically just what's within the brackets, right? Given and what, so they've termed B the modularity matrix. So B is something that is just purely empirical. You just know this is my network. Okay, I can find B. Okay, because there's no assumption of anything gone here. This is just purely empirical. So knowing B, I need to now find S such that my Q is maximum. Okay, so that's the question. So how easy that question is a different story, but that is the question. So the question is, how do I find S such that Q is maximum? One of the most widely used approaches, which is sort of outlined in these two papers for undirected and directed networks, is just based on the insight that the optimal S would actually just be an eigenvector of B, right? So remember, so if S here is just an eigenvector of B, then you get what? You get lambda times S, the lambda comes here, then S transpose times S is just N, right? Because basically you just multiplying each sort of spin by itself and just get, so -1 times -1 +1 +1 you just get N. So you get lambda times N by 4m. And now you just say, okay, fine, I need to maximize Q, which means I need the highest eigenvalue. So if I just find the eigenvector corresponding to the highest eigenvalue, and that I'm done. But the problem is S cannot be any eigenvector. S has to be only +1 or -1. So I have to have the S which comes close to that. So those details I'll skip for now, but that's the insight over here. So
is S like something that exists per group or per partition?
No, S is for the whole network. S is basically is the list, or is a vector that's telling me for every node in this network, am I belonging to group 1 or to group 2? So this whole procedure is just to first divide it into 2 groups. So we do it groups at a time. So suppose I want to subdivide it, then I take subgroups and then so on, and I define it for that. So basically for a given group, how do I split it? That's what the S is going to tell you. So I won't get into those details for now. But maybe what I'll do is I'll just give you an example just to show that how powerful this approach is. So that specific method that I just mentioned. So we actually had done this on the network of connectivity in the brain. Okay, and so with the data that you can that tells you about which brain region is connected to which other brain region, and this is for the case of the macaque, the monkey. You can actually just try to figure out what are the communities. So which parts of the brain are more connected to other parts of the brain, right? And it turns out that actually when you do this analysis on the network, it has roughly 5 modules or 5 communities, and that's basically just a list of all the brain regions that are seen within each community. And as we talk about over here, there is sort of a kind of a relationship between the composition of each module and sort of a sensory modalities, basically in terms of the different senses that our brains are involved in. But I'll leave those details for now. That's not important. The important point is that this technique is actually very powerful and can lead to a lot of very useful insights in real data.
So normally usually when you are trying to form these modules, you will start with two groups and then make some, or you will do another kind of algorithm to find these modules.
No, so at least I will say for this particular approach over here, what is done is that is say, or let's do an initial division. So initially, it's clear that we can divide this into two groups, and then let's just see what nodes would belong to each one. Then we see can we subdivide the groups, and so on. So that's how this procedure works. So, but you can have other approach. I mean, there are a lot of different ways by which we can do it, but this is like one of the most sort of common ways of doing it.
So this 5 modularity that you got in these,
Yeah.
it is not coming from this kind of algorithm.
Oh, it is. It's just that here I didn't give the full details of this algorithm. This is just the first step. This is just how you do the initial division. Then you have to do some subdivision. Then there's also some refinement steps, because you also, like, once you divide, you might not want to keep that as the final set. You might want to just try to shift some nodes back and forth just to see is that going to increase my modularity. So there are a few subtle details that I didn't want to get into here. But broadly speaking, this is the idea, right? So yeah.
If we use this maximization
Yeah.
on a network that has multiple modules, it will give the most modular component and then rest of the components as.
So what it will do is assuming your network has the modular structure, what it will do is it will try to identify what are the groups where within each group there is a lot of connections. That's what it does. And
It will give two groups, right?
this details over here is how do I divide a group, or is it possible for me to divide a group? So as I said, it's a sort of a recursive procedure. So I do an initial division, and let's say I'm able to get two groups successfully. Then I go to each group and say, okay, can I divide these groups as well, and so on. So it's like, so there are more details which I didn't want to get into, but yeah, so that's how you do this. So you can do this for any network. But of course, an important point which I should mention is that this need not give you the maximal queue, which means that this might not necessarily be the most optimal partition. It does a very good job. In most cases, this technique is quite good, but remember this is a very high dimensional sort of space that you're working in, because there are all sorts of combinations by which you can arrange group nodes into groups. So there might exist some grouping where the queue is even higher. And to do that, you will need to use techniques like simulated annealing, which Anuran will be talking about tomorrow. And in fact, speaking about that, we actually use that over here. I won't mention the details simulated annealing, but this is just another sort of structural attribute similar to modularity but different in a way, which one can use a very similar approach to try to uncover the structure. So this is the last thing that I'll mention. So just like a modular structure, a network could have a hierarchical structure, what's called hierarchical structure, if there exist layers of nodes such that the density of connections between consecutive layers, so basically between say purple to yellow, yellow to red, red to blue, if that is higher than that, let's say within the layers, so say between the red or between non-consecutive layers, let's say going from blue to yellow or from purple to red or something like that. So essentially you have a lot of connections. So basically you can think of them as sort of like having a kind of a linear structure. You basically have some nodes, some nodes, and then you have a lot of connections between these layers. But of course, that's not the only type of hierarchical structure. You can have other types of hierarchical structure as well, but this technique can in principle be sort of extended to other types of hierarchical structure. But for this case, let's just consider this very simple linear hierarchical structure. All right. So with this linear hierarchical structure, now how does one see whether or not a network has a structure like this? And it turns out that actually you can use almost exactly the same approach as before, but this is a slight tweak to it, right? So remember, for our queue, we had this, right? We had basically, so remember what this is. This is just the excess number of links within a group, right? We now, rather than excess number of links within a layer, we want to see if there are excess number of links between two layers, right? So basically going from Li to Lj, from L and Lj and vice versa. So basically, by having that constraint, we can now once again compute this the excess number of links, and this parameter is what we term as the hierarchy index. So this is very similar to the modularity, except now rather than looking at connections within the group, looking at connections between layers, right? And so maximizing H should in principle lead to an optimal hierarchical decomposition of this network if it exists, right? And so one can of course use like an approach similar to what I just mentioned before, where one basically looks at the eigenvalues and so on, but there is, as I said, a better way, or at least a way that might lead to an even better decomposition, which is spectral method, where basically one simulated annealing. But before that, let me just mention the approach. So you have some network like this. Okay, so I have no way of knowing if this is hierarchical or not. And what I need to do is I say, okay, fine, I assume that these are the layers. Then I just so I start with this, and then I say, okay, fine. So a node I can swap nodes between layers, I can split layers, I can join layers, and also I can rearrange layers. Okay, I can do all these possible steps, and I keep doing these steps and seeing, by doing this, is my H going up or going down, right? So if my H goes up, I accept this and say, okay, fine, this is good, and now I will go on from there. But if my H is going down, then with some probability which is based on some temperature, I will accept it. And the details is, so that's basically the simulated annealing procedure. I won't get into the details, but basically it's just that. So if it increases the H, accept it. If I don't, then and so
this is similar to what Rajesh was discussing.
Yes.
The metropolis level.
Yeah, it's similar to that. Yeah.
Except that here you decrease the temperature gradually. So you start with very high temperature, then you gradually decreasing temperature. So the idea is not to get stuck at some local pocket.
And so basically, as a result of doing this iteratively, you'll find that with the same network, follow this procedure, you end up with something like this, right? And you can see here, this is the adjacency matrix. You see that these form like layers, basically. So between layers, you have connections going from layer 1 to layer 2 to layer 3. So it's not along the die, because so within each layer there's not much connections, but across from adjacent layers you have a lot of connections. So it's quite remarkable how you can actually uncover this sort of structure with a very simple sort of constraint. And it turns out that we take the same network that we had looked at earlier, and we just say, okay, does it have a sort of hierarchical structure? And it turns out that for this particular network, it just so happens that yes, it does also have a hierarchical structure. In fact, it has like a bunch of layers. And I mean, so I won't get into the detail, but what we termed is that it has modular hierarchy, because we already know that it has modules. And we also know that it has a hierarchical structure, and in fact the hierarchy is sort of embedded within the module. So you see here that module 1 has like the first few layers, module 2 has another layer, a few layers, and so on. So it follows it almost remarkably, yeah, so this is something that we were also looking at. And so because the simulated annealing procedure is stochastic, we do over many trials, and then we see like what is the decomposition we get every time, and this is again remarkably consistent. It turns out that time and again we keep getting the same layers occurring in the same part of the sequence. So, but anyway, we can talk about that more later, because I don't want to think. But so basically the point of explaining this is just to say that there is still so much sort of work that one can do, and this was actually as you can see, a very simple extension of the idea that was proposed by Newman, and you can still get so much other useful information from these real world networks. So yeah, so I guess the take home message is that there is still so much work to be done, especially in fields like network neuroscience. So much information that one can still extract from this empirical data, and so I think maybe I'll just end with just a list of references. So I'll put them up on the site as well, not the books. Well, this book, I mean, this book is actually freely accessible. This book is by Barabashi. It's you can just go to the link over here and get it. If you can get access to Newman's book, you should. It's very good. And yeah, so basically these are things that you can read up later, and any more questions, just feel free to talk to me at any time. Thank you so much. Yeah.